Everyone, I'm Sion from the SLAP research group at KU Leuven, and I will be presenting our chapter called CTAM, a tool for continuous threat analysis and management. We've already had several presentations here today referring to this picture as well, so I don't think I need to provide that much context here about the DevOps lifecycle. But it's important to note here and a concern when we want to perform threat analysis, how do we deal with this kind of fast-paced development with frequent iterations that introduces some challenge, especially when we want to do threat analysis and management. And we'll go into a bit more detail about what those challenges are. But before that, I want to briefly refer to why we want to perform threat modeling, do an analysis of our design. And when we look at the latest iteration of the OWASP top 10, we see that they now explicitly mention insecure design as a top 10 issue. And zooming a bit more into that description, they refer to more attention that needs to be spent on focusing on risk related to design flaws in the system. And they explicitly call out the need to perform more threat modeling. So that's really something that we need to take into account also in this kind of development context. And when you want to apply these techniques, and having this kind of support allows you to reason about a number of important concerns, like what is the progress that you're making in addressing different kind of threats? How is your risk evolving over time? Are you making progress in the right direction? Are you addressing the key threats, or do you still have a lot of open issues? But also, what is the impact of proposed changes? Of course, there may be several features that are being developed in parallel, and what would the impact be of integrating those changes into your project? Do they introduce some important new threats, for example? So these are all very relevant questions that we want to be able to answer in such a context. And to be able to think and answer these kinds of questions, we need to perform very frequent threat modeling to find these kinds of flaws in the system. So threat modeling is really a good technique to do a very systematic analysis of the design of your system. Now, the problem with this technique is that it's often a manual exercise. So it's performed by people that really sit down, do the diagram, and do the analysis manually. And that, of course, makes this type of assessment very slow and expensive. And as a result of that, it's very commonly a single-shot effort. So you do an analysis once, and then hopefully you do something with the results. But with a fast pace in development and frequent changes and iterations, of course, that analysis that was performed in the past is not very representative anymore for the current state of the system. So we need something better for that. Another concern here is the reliance on security experts. That's a very scarce resource. You don't have a lot of them available. So having to perform these kinds of assessments manually is also suboptimal, of course. So when we look at existing threat modeling tools and how we can embed them in this types of development lifecycle, we see that many tools still rely on manual elicitation, such as ThreatDragon and ThreatSpec. So that's not really useful in this context when we want to automate things as much as possible. There are several tools that allow automation as well, but I will go into a bit more detail later on and why some of these tools are still suboptimal for integrating in this development context. There's of course also a whole body of other techniques that we've seen also in the previous presentation, like static and dynamic application security testing, that are very complementary to this type of analysis, where we both consider the code and implementation level vulnerabilities and the design of our system itself. We want to leverage tool support as much as possible in this kind of context to reduce the manual effort that we have to spend on this type of analysis. And for that, we want to leverage existing analysis tools, of course. That introduces some requirements on the types of tools that we need to be able to integrate them. So we want them to to elicit all the threats that we have in our system, also threats that we have mitigated, because we want to keep track of this effect actually that we're mitigating certain threats. If a tool would no longer elicit those threats because we have some countermeasure, we cannot take into account this effect over time that certain threats have been mitigated. So we kind of lose that information to keep track of the progress that you're making. And of course, we want to be able to run this automatically as part of CI/CD pipelines so that we can really automate this and frequently reassess our model. So what is the approach that we took? We decided to version the design model that we use as part of the threat analysis together with the code in the repository. So this allows us to keep the model of the system that we use in our threat modeling analysis, to keep that together with the code, a specific version of the system it refers to. This also kind of gives a trigger, an impulse, and reminder to keep also this up to date with how the application is evolving over time as changes are made. And the second element is that we want to keep track of the results and link them to the particular source code commits. And having both these elements allows us to track the threat mitigation progress over time and see how these results evolve when they're making changes and the improvements. So as I mentioned, we need some kind of threat modeling tool to automatically apply in this context. And as I've mentioned, the manual tools, of course, cannot be used here. The same problem occurs from some automated tools if they remove mitigated threats, because we don't have this information anymore to keep track of the progress that we're making. Additionally, we want some kind of richer information about the results as well, so that we can use some risk values. What is the percentage that were of threats that are mitigated? So the richer results that we get from a tool, the more information that we have to work with to calculate some aggregated statistics and overview of our results. So for that, we leverage the existing engine of the Sparta threat modeling tool that we developed ourselves, because we have all this additional information available to use. So let's zoom into a bit more detail in the information that we have as part of this analysis. So as a main input, you have the model itself, a data flow diagram of the system, and we enrich this as well with different kind of security solutions. So this allows us to keep track of the different mitigations that have been added as well to address certain threats. And from that input, the tool will analyze it and will give you a list of threats. And in addition to that, we have a number of risk values. We have the inherent risk. So this is the risk assuming you don't have any countermeasures at all, if you would be fully vulnerable, and the residual risk that takes into account the effect of the different solutions that you have in your model. So that allows you to really see what the impact is of certain countermeasures that you have added to your system. So with that, we can move on to an overview of our approach, the complete picture. So I will zoom into each of these steps in a bit more detail to explain what is going on. So the first step is committing the model together with the code in the repository. So that allows us already to track the evolution of the design of the system. And with this push to a repository like GitLab, we can automatically trigger CI jobs to run this analysis on the version models. So for this, we created a Dockerized version of the threat modeling tool to run the analysis and submit the results. Then these results are collected by a server component, and they are linked to the particular commit for which the analysis was run. So this way, we really know that particular version was analyzed, and these are the results of that particular analysis. And collecting all those results together, we can present all that information in a dashboard to the user, and that allows us to provide some interesting insight into the progress that is being made in the project. We'll give a brief overview figure of types of patterns that you can see in how the risk evolves. So depending on whether you make certain modifications in the system, you will have different kinds of effects that you see in the risk. So if you add, for example, secure functionality, you will see that the inherent risk would rise, of course, but your actual residual risk stays the same because the functionality is properly secured. And of course, depending for different types of changes, we will see different types of patterns emerging in your results. To plot that more into an overview of how that can change over time, I have an illustration here how you can see how different types of changes will be visible in these kinds of aggregated overviews. And when you have that information, that allows you to answer some questions regarding your threat management and the progress that you're making. So you can see whether the measures that you've introduced or whether they are really effective in reducing your risk, what the progress is that you're making in mitigating different threats. And of course, you still have the detailed results of every analysis as well. So you can still look at what are the most important threats that we have for this particular version of the system as well. We did then a functional validation of the system on a design of a document processing and delivery service. So this was part of an earlier research project as well. And here we made some particular changes. So you see that some elements here are in gray. So that's just to visualize modifications that we make. So that can be adding a new third-party integration, adding some additional functionality and storage. And with those different versions, we then ran the analysis on these modified models, and then you can see similar patterns emerging in the data as well. Now, this was a very simple diagram. We also applied this on a more complex diagram that is derived from a real-world application. So we had a student as part of a master thesis project create different versions of the server components in the corona-borne contact tracing application. So just to give you an overview of all these different versions, you see here the full list. So every time there was some significant change in one of the server components, a new version of the total model was created. I can also give you an overview of how you can see how the complexity of these types of models changes over time with a lot of new elements, data flows, and processes introduced. And on these models, we did a similar analysis to uncover these types of changed patterns in the risks that were identified. Of course, this is not the end point. There's still a lot of open questions and interesting future research directions to address these problems and enable a further integrations and reduce the effort in constructing these models. So one element is the input model accuracy, of course. So at this stage, we still require to manually create that model and keep it up to date over time. There are some approaches already available to help in reducing that effort. So one option is to embed the model in the code. So you could use source code annotations to keep that information really closer with the source code of the application itself, or there are text-based representation that may also prove useful in capturing this information. Other approaches are to do conformance checking, so verifying also, that could also be an analysis job to verify whether the model actually corresponds with the implementation itself. So you could try to detect whether there's some drift or some changes that do not accurately reflect in the model. And then a more automated approach to fully reduce effort would be automated reconstruction based on source code analysis as well. And that would, of course, avoid that initial modeling effort altogether. The second element is the analysis activity. So we currently can see the progress that we're making in mitigating different threats that were identified in the system. But there are different kinds of analyses that you can perform based on all that data that is collected, that historic information for every version of the product that is analyzed. So an example I already gave previously is assessing what the impact is of certain feature branches and see if those are merged in the main project. What would be the impact on our list of threads and on our aggregated risk values. But you could also do other interesting longitudinal analysis. Do we see that certain security solutions that we have previously applied in the past, do they indeed have the intended effects, or they're effective at addressing the threats, or do we see that some solutions are not working very well? So it's a rich source of information that you could use for other types of analyses. And then the final element is the metrics themselves. So currently, we calculate the amount of threats. We have the inherent and residual risk. We have some information about how the model evolves in complexity and size. But these are probably not the only relevant information that you could calculate based on these models and these threat analysis. So we think that having this historical information also and these results could make it easy to evaluate different types of metrics as well using the same data and see, do those metrics maybe give you more or better insights. So it's also an opportunity to further explore and evaluate other types of metrics in this context as well, because it remains a challenge, of course, in how to measure the security and how to get a good insight of the progress that you're making in addressing these types of problems. So with that, this CTAM tool, we provide a first step towards a tighter integration of threat modeling and code. We make it an active concern to keep this model version together with the code. There's several opportunities to get that model from the code with automatic extraction, with annotations that can further reduce the effort in maintaining this model over time and ensuring that it correctly corresponds with the application. But we think this is a good first step towards considering threat modeling as a continuous concern. So to really keep assessing and ensuring the security of your system and the progress that you're making in different threats. I think I have a bit more time, so I can give you a quick demo as well as a tool. So I have a local version running, and I think that can illustrate some of these elements. So you have an overview of the project, so you can also aggregate over multiple projects as well to see what your total state is in addressing different risks. And then you have, of course, the analysis results of individual projects where you can see the evolution of your project in amount of threats and how your risk is evolving over time. So ideally, of course, you want your residual risk to decrease over time. And you can also just look at the progress that you're making in reducing risk. So are we appropriately addressing all the issues? And you can keep track of what are the results of the latest analysis. So are there any new critical threats popping up in the latest version of the system that requires some attention? And of course, all these results are linked to particular source code commits, so you know what the state is in a particular version, and then you have some additional metadata, of course, to give an indication of the size of and complexity of the system and how many countermeasures were introduced. So with that, I think I'm right on time to end my presentation. So thank you very much for your attention, and I'm